number of radial ducts, number of stator slots, and the number of turns per phase. Number of turns per phase of a 3.7 kilowatt 4000 volts 3 phase 4 pole 50 hertz squirrel cage induction motor. Okay, SCIM to be started by a star delta starter. So work out the winding details. Take average flux density. Take average flux density in the air gap is equal to 0.45 Weber per meter square. Okay, ampere conductors per meter is ampere conductor per meter is 23,000. Efficiency of the machine is 0.84. Power factor is 0.84. Winding factor, that is KWS, is equal to 0.955. Stacking factor SF is 0.9, and your L by Z, sometimes it will be L by tau, or some books will write L by Z, is equal to 1.5, where this tau is equal to Z is equal to pi d by p. So this you should, it's not given in the question, you should know this. Okay, so first of all, like doing this question, so we have to go about this question. So main dimensions, what it is asking us to find is, so given data we know. First we'll write the given data, what is the data that is given. So if you go look at the problem, so first of all you have to go determine the main dimension, the number of say stator slots, the number of turns per phase of a. So as far as the power of the machine is concerned, so it's a small machine, that is 7 kilowatt only. Okay, and then the voltage of the machine is 400 volts. Okay, number of poles is equal to 4. Frequency is 50 hertz. Okay, and it's started in star delta starter. Okay, so on the, when you have to go for calculation of the voltage level, so at the secondary side you notice it started in delta, so you have to, in delta your V line is equal to V phase, so that is important. If it was delta star, then you had to divide by root 3. The secondary point would be essential over there. So now what it is given, flux density in the air gap, that means BAV is equal to 4.5 Weber per meter square. Your ampere conductors is equal to 23,000. Your efficiency is given 0.84. Power factor also 0.84. Rest data is here. Okay, same thing, rest you know. Now what you have to find, See, now the number thing, D you don't know. Main dimensions would mean D and L. Determine the main dimension. So this is D and L. Number of radial ducts. Then you have to find the ducts. Number of radial ducts. Now I'll explain you. Number of radial ducts and number of stator slots. Stator slots means what? Huh? That is your SS you have to find. Okay. And the number of turn per phase. So TS you have to find. Okay. Threefold. Work out the winding details. Then you have to work out winding details. So first let's read the problem. You take down the problem in your notebook because if you once you take down this problem in the notebook, then it will be very easy. The problem will be always in the front of your page when I'll be doing this question. So as far as the question is concerned, so we know that d square L value we can find out. Yesterday also we saw how it can be found, how it can be easily found out. So the first thing we'll do is that we know that this d square, this is the solution. Okay, so we know d square L would be equal to Q C naught NS. So this is the formula we are having, where this Q would be equal to your input kVA. So input kVA. So tell me the formula of Q in terms of kW. Q would be equal to kW divided by, tell me, yesterday also we did a problem, divided by efficiency into cos phi. This would be kW efficiency into power factor. So kW value you know is how much? 3.7. That value is equal to, by this time you must have cap 3.7, efficiency 0.84, again power factor 0.84. So this value would be around 3.7 divided by 0.84 divided by 0.84. So this will come around 5.182. Okay. Now C naught value again you will calculate. So the C naught value which you will be having is in terms of 11. If you write like this, 11 into BAV, here this AC over here in the problem, this can be represented also as Q na. Q is equal to 23000. This is represented as Q also. So this is ampere conductors, AC or Q, whatever you want to write, you can write kW in 10 power minus 3. So rest values we have, BAV value we have 0.45, Q value we have 2300. You have the value of kW in terms of 0.955, then you have in 10 power minus 3. So you get one particular value, so it would be around 108.73. Then synchronous speed is equal to 2F by P. Okay, so this synchronous speed 2F by P would be 2 into 50 divided by the number of poles, so it would be around 25 RPS. Now again, if you see here, you have all the values. D square L Q value you calculated just now, that was around 5.182. C naught also you calculated 108.73, and NS value also This is in this formula. NS value also, this is 25. So tell me the value. What value you are getting? Hmm? What? Calculate this. Yeah, Manohar, Ratika, Afsa, yeah, Nilinakshi. Calculate this value.
1.93 into 10 power minus 3.
Yeah, 1.93 into 10 power.
Minus 3.
1.93 into 10 power minus 3 meter cube. Okay. Now again, what other values you have? See, till yesterday, at least main dimensions everybody should be able to do, because yesterday we did a similar problem. Okay, similar problem, but here there are certain other factors they are asking, but main dimensions. Now L by Z ratio is also given. L by Z is 1 by 2. Okay, so L by Z ratio also given. L by Z is 1 by 2. That would mean L by Z 1 by 2 would mean basically Z is what? Z is pi d by p. So that means Z is equal to pi divided by 4 into d. So pi divided by 4, tell me what is the value? Pi divided by 4. So L by Z ratio here is not 1 by 2. You just carefully see it's 1.5. In yesterday's problem it was 1 by 2. So here it is 1.5. Hmm. In this particular problem it is L by Z ratio is equal to 1.5. So the value of L in terms of Z, if you want to see, would be equal to L would be equal to 1.5 into pi d by 4. This is the value. So finally you get a value over here. So this value will be around, tell me how much? L would be equal to 1.178 d. So this is the value that I'm getting. Okay, so I have this L and this ratio, I have d square L ratio. From this equation 1 and then equation 2, I can get the value instead of d square into, substitute the value of L in terms of d, that is 1.178 d is nothing but equal to 1.93 into 10 power minus 3 meter cube. So this value, from here we can get the value of d, get the value of L after substituting here. So please get the value of d and L and let me know. So what is the value of L you are getting? What is the value of d? So I am getting the value of d as here. So the value of d that I got is around 0.117 meter, and the value of L, that is 1.178 into 0.117. So this would be around 0.134 meter. So this is L value and this is the Z value. Hmm. In terms of millimeter, it would be around 134 millimeter. Okay, because we have to divide by multiply it with by 10 power 4. 10 power 4. 1 meter would be equal to 100 centimeter and 1 centimeter is 10 millimeter. So it would be 1 10 power 3. 3. Into 3. 10 power 3 we have to multiply. So 1 meter would be equal to 1000 millimeter. So in terms of millimeter, it is what L is equal to 134 millimeter. Now it has asked about something called as radial ducts. It is asking for the radial ducts. So what is the radial ducts? See, if the core length, now we are seeing the length of the core is exceeding 134 millimeter. When in the beginning sessions, if you go back to the video lectures, there also in the live session, the contents material, some of the videos are there in the YouTube, but in everything is there in your content section. So there also live video recording has been put. If you go to the earlier session, some of you who might have missed the classes, so there I have mentioned about this. So if the core length will exceed 125 millimeters, so if the core L, that is the length, exceeds like 125 millimeter, so radial ventilating duct should be provided. Because why radial ventilating ducts need to be provided? What is the reason why? See, what will happen is the machine heats up. So in order for the machine to cool down and not burn out or not result in a short circuit or due to heat, so you need to cool down the machine. So if you carefully look even at the transformer outer side, like we have also studied that cooling tubes are provided over there. Okay. And in your previous semesters also you have seen the method of oil and other factors involved to cool it down. Similarly in this also, so we need to provide radial ventilating ducts. And one more important factor over here is, and and the width, the width of these ducts should be around 10 millimeter wide, and the width of these ducts should be 10 millimeter, should be 10 millimeter wide. So this we came to know. Now we just saw the length of the core is 134. Therefore, see, if therefore we can say that if above 125 to 134, 9 mm is there, and 9 mm means almost equal to 10 mm. So we can say the length of the core is 134 mm. Therefore, one radial ventilating duct 10 millimeter wide is sufficient. So I'll write down the length of core is 134 millimeter. So therefore, one radial one radial duct of 10 millimeter width is needed. Okay, so that is there. But one more thing is that the all the iron involved in that we don't utilize it. So the net length of iron that we need would depend upon the certain factors. That factor would be like you have to like minus those percentages, so you don't efficiently, because there is some air gap. So that overall net length of the iron, I can write down net length of iron that I need would be equal to a factor called Ki. Okay, that is usually 10% wastage would be there. Like in the making, if you have some material, if you are forming into something, you cannot utilize the entire material. Some material will go down with grazing and other things. So that thing we have to take into account here. Like 90% we'll utilize. So this factor would be zero point 0.9, and then we have the actual length, that is 134 millimeter, minus how much width is required, minus 1 into 10. So this is the actual length which we needed, 10. Although The difference between these two is only zero point 0.9, but the actual length is required 10. So the total length at the what we'll get, the net iron length would be around 11.6 millimeter, or around 0.11 meter after this calculation. So this is the net length of the radial duct. So this is if you look back to the problem, so we have also calculated the number of radial ducts. Okay, so basically only one duct is required, and the length of the duct would be how it is established in the examination. If you leave it at that point also, it is good, because they have not asked for the length, but I have given you in some exam they may ask you for the length also, so you can calculate this. Now the third part of the question is the the number of turns per phase. So again, turns per phase is just like the tomorrow's yesterday's problem. So again, you can do it. It's very simple. So as far as the turns per phase is concerned, so now the third part of it is how to calculate the number of turns per phase. That is your TS value. So in order to calculate the TS value, you know that your E phase is equal to EL, that is equal to 400 volt. So now we have to calculate the ES value. So you will calculate the ES value. See, you know ES is equal to 4.44 F pi TS kWs. So TS value, if you need, TS would be nothing but ES 4.44 F pi F5 and kWs. So all the values, ES you have, kWs you have, F you have, but you don't have this phi value. But we what we have is that we have BAV value. BAV value is there, it is given. BAV is 0.45 Weber per meter square. So from this BAV you can calculate phi. Okay, because what is basically BAV? BAV is phi by A. Okay, this is the area. Okay, so area per pole. Area per pole, yesterday also we saw this value. Area per pole would be equal to how much? See, it's a cylindrical cross section. It will be basically pi dl, and per pole, that is P. Okay, pi dl P. So you can write down your BAV value would be equal to phi divided by pi dl divided by P. So this essentially, if you see, look at this formula, we have utilized in DC machines, transformers, everywhere we have used this particular formula. So we have utilized this formula everywhere. So we will resubstitute these values and get the value of flux. So if you want to get the value of your flux, so the flux would be equal to BAV pi dl by P. So your BAV value is how much? 0.45. 0.45. This would be equal to 0.45, 0.45 into pi. D value you just calculated was equal to 0.117. You have this p value as 4. Okay, and L value 0.134. So so you now have the value of phi, that flux value. So flux comes around 5.538 into 10 power minus 3 Weber. So this is the value of the flux that you get. So now you have to calculate the number of stator turns. Now in order to calculate the number of stator turns, TS would be, again, TS is equal to, from the previous equation that I have written over here. So TS substitute here in this particular equation. So TS is equal to ES 4.44. So here ES 4.44 F by kWs. So ES would be equal to E line is equal to E phase. So your ES value would be equal to 400 volts. So this is your 400 divided by 4.44 into F is 50 into your flux you just now calculated, that is into 5.538 into 10 power minus 3 into kWs value is given 0.955. So you get a particular fraction would be there and you take the nearest integer value, so that you will see after substituting this, so you'll get a fraction value, but you have to take a particular integer. So the number of turns here would be 341 if you calculate. Now again, if you look at the problem, so let's go back to the problem. Determine the main dimensions, that is your D and L. We have answered to this. Number of radial ducts, we have answered. Number of stator slots and the number of turns per phase, we have answered to this, but now we have to calculate the SS. So number of stator slots, so from TS also we can do it. Now TS is equal to, see, if you want to write the value of ZS, ZS would be 6 times TS. So basically what happens is the number of phases and number of poles will remain same as usual in the yesterday's problem. 3 into 4, that is 12. So the number of stator slots per pole per phase QS should be either equal to or greater than 2. Otherwise leakage reactance will be high. So usually what, whenever you are taking the number of stator slots, so there is one particular thing that you have to keep into account. So in order to take the number of stator slots, so number of stator slots, if you have to consider the number of stator slots, what you have to do, the number of slots per pole uh, and per phase, that is your QS, should be always greater than 2. If it's not greater than 2, what happens is that your leakage reactance will be high. So the reactance, leakage, if it is high, your efficiency of the machine decreases. The leakage reactance will be high. You don't want the leakage reactance to be high. So let's start QS is equal to 3. Now you have to understand your stator slot pitch. So what is your stator slot pitch? Stator slot pitch. So your stator slot pitch, how does it read? It is like, it's written like this, and that is nothing but your pi d, that is circumference, divided by the number of stator slots. So the number of stator slots would be governed by the stator slot pitch. So the number of stator slots, if you have to take into account, that is SS. So this SS would be equal to number of poles into number of phases into your QS value. So QS is what? Okay, QS has to be greater than or equal to 3. So here you see this number of poles are 4, number of phases are 3. This is a static quantity, so always you get 12. So first value you will get for stator slots is 36. So the second value will be 12 into 4, that is 48. So third value would be 60. Fifth value would be 12 into 6, 72. Okay, so this is first, second, third, fourth. So here, like, instead of into 3, we will do into 4, into 5, okay, into 6. So it's like that. So this would be common. This would be common. So now, in order to judge, like, this is a small machine. Yesterday we saw a 250 HP machine. This is a 37 kilowatt machine. And usually this type of machine is an open type of machine. So slot pitch for open type slots is equal to 15 to 25 millimeter. Okay. Slot pitch for semi-closed slots is less than 15 millimeter. Okay. So yesterday, if it's a big machine, that is like is an open type of machine. Already, I have discussed this in the theoretical part. So, and big machine means it should be greater than 100 HP. Some numerical value is there. Please look into that. Okay. So here, I'll again write down for your convenience. Slot pitch for slot pitch for open type slots. This is for open type slots would be around equal to 15 to 25 mm, and then slot pitch for semi-closed type slots, this is B, that is the slot pitch for semi-closed type slots. So this slot pitch for semi-closed type slot should be around uh, it would be less than, okay, 15 mm. So therefore, since it's a small machine, so what we do is that therefore select slot select slot pitch for semi-closed. So that means this value has to be less than 15 mm. So let's check with the first value. When we are putting the first value, so pi d by ss over here. So first value pi into the diameter 0.117 divided by 36. When we are doing this, we are finding 10.2 mm. This 10.2 mm is less than 15 mm. So this is good. So this is working. And number of slots is only 36. So we need not go to check for other slots because already we got lesser number of slots. Lesser number of slots means the cost will decrease. So this is okay. With our first value only, we got the perfect match. So the number of slots would be equal to around 36. Now, as far as the total number of stator conductors are considered, so the number of turns per phase which we saw over there was 341, but the turns per phase, as it should be always an even number. So we will take the next even category because see, it has to be the turns per phase cannot be an odd number. So this is the turn. Okay, we cannot have a turn like this. Okay, it has to be a full turn. So that's why we cannot leave it as this. So it has to be this. So the winding, if you see how it's wound, there's one type of winding is like this. Okay, this is called the lap type of winding. Okay, this is the lap type. Another type of winding that we are doing is a wave type of winding. So where this is a wave. Again, similarly it will go like this and this. Okay, so this is a wave type of winding. So the number of turns we are interested in. So the total number of conductors, that is total number of conductors, that is our ZS would be equal to 6 times of TS. So this would be 6 times of 340. Let's suppose this is around ZS value. If you see 6 into 340, so you'll get around 2040. 2040. From here, if you want to calculate the stator slots, so see ZS is equal to SS stator slots into ZSS. ZS is conductors per slot. So this value you calculated 2040. Okay, and stator slots 36 that has been calculated. This is ZSS. So the ZSS value from here is equal to 57. So let's see, okay, the actual number of stator slots, do they match? So if you write again the actual number of stator slots turns per phase, that is in terms of turns per phase, so that would be around ZS into SS, okay, divided by 6. So that is the same thing, you will get around 340 turns from this also. If you put substitute the value back, ZSS value, if you write the ZSS value, you write the SS value, because ZSS value is just not calculated. This was equal to 57 into 36 divided by 6. So it will be around 342, which is nothing but as equal to 340 only. Same thing, 1 or 2, it will not affect much. So the thing is that now you have calculated the machine. Now you have also calculated the what you wanted stator slots also you calculated. Okay, that was 36. Even you calculated ZSS also. So no problem. I was telling you, if they ask you that also, see number of stator slots. Okay, uh, ZSS, if they ask number of stator slots, and if for example and conductors per slot, although they have not asked in the question, if they had asked, so this ZSS over here, ZSS value is basically what? ZSS is, see here, ZSS is equal to conductors per slot. Per slot, SS is equal to stator slots, and ZS is equal to total number of conductors, which is nothing but this is equal to ZS equal to ZSS into SS, and also this ZS you can write 6 times TS in case of three phase. In case of three phase, now if it is single phase, then it is 2 times TS in case of single phase. Okay, so phase you can write like this also, no problem. So now the final thing, it is asking, tell me the winding details. So something they can also ask in some problem, they can ask you coil span. Okay, CP, coil span. So this coil span is equal to number of slots divided by 2. So number of slots divided by 2. So the number of slots, if you see, are 36 divided by 2 is 18. So what does this mean? This means, see, if you have this construction 1, okay, and you have like this, you have like this. So your one winding, okay, the one winding would be connected with the 19 winding. The second winding would be connected with the 20 winding. It is, if it is because if it is full pitched means, full pitched winding means if the number of coil span will end after the total, let's see, if there is the coil span is 18 and it is connected, like first slot is connected to the 18th slot. Okay, suppose it's 36 slots are there, so it's a full pitch winding. So that means it will start from 1 and at 36. So and between 1 and 18 there would be 1 and 19 there would be a coil span. So basically, the one more essential thing over here they have asked, uh, is machine drawing this year in your semester or next year? Electrical machine drawing. Tell me. Ratika, Ratika,
Yes, sir.
is machine drawing this year in your semester or next year? Are you studying?
We don't have this sum.
You have a computer aided drawing of electrical machines, CADM.
No, sir.
That means so I think they will avoid to ask this winding details, but still I will explain because earlier it used to be in the same semester, so they used to intermix. They used to ask. So although I will explain you this because so as far as the this thing is concerned, so number of coils per phase. Now you just came to know that number of coils are 18. So number of coils is equal to 18. So one important thing is that for the winding details, winding details we have for small machines, like very small, for small machines, single layer winding is used. Single layer winding. For large machines, yesterday you saw it was a large machine. What type of winding we employed? Double layer winding we employed. Okay. And what happens in a single layer winding? So, see, the difference between a single layer winding and a double layer winding is in double layer winding, in double layer winding, see, in double layer winding, number of slots would be equal to number of coils. Okay. If you go back, revisit to yesterday's problem, okay, you will find out number of slots is equal to number of coils. Now, in yesterday's problem, yes. Now in today's problem, we have to taken it as single layer winding. In single layer winding, number of slots is equal to number of coils, number of number of coils is equal to number of slots divided by 2. So here it would be 36 by 2 is equal to 18. So now basically it is a three phase machine. So number of coils per phase. So number of number of coils per phase, number of coils per phase. What is one second? Yeah. Number of coils per phase would be equal to 18 divided by 3, that is equal to 6. So number of slots per pole, see, number of slots per pole is equal to 36 divided by 4. Number of slots per pole would be equal to 36 divided by 4, that is 9 slots. So if you have to go for the actual coil span for this machine, that means it is actually therefore the coil span for this machine is 9 slots. So 9 slots. So that means what? The coil span, because it's a three phase, is, I am sorry, okay, something is there, some mistake. Okay, yeah, I'll take in the next slide. Something is happening. Yeah. So that would mean the coil span is 9 slots. So therefore the coil in slot 1, coil, total number of slots are 36. Coil in slot 1 is connected to coil in slot 10, because you just found the total number of the coil span to be 9 slots. Now the number of slots, that is 36, per pole divided by 4 into per phase, that is 3. So this is slots per pole per phase is equal to 3. Here you can see 36 divided by 12 is 3. So how do you write down, because it's a three phase machine? So in a three phase machine, in order to write down a three phase machine, you have the three phase as this R, Y and B, and this is separated by 120 degree, 120 degree, and again a 120 degree. So this would be basically essentially, if you have three voltages, if this is ER, this is EY, and this is EBE. Okay, so the angle, there would be an angular difference of 120 degree. So if you have to draw the winding diagram, okay, now let's draw the winding details, what the slots allotted to the three phase. So we will write the slots allotted to the three phase. So we have the slots allotted to the three phase, so we can write go by R, B and Y. So if the first slot is connected to 1, okay, so we will see for each phase, see slots purple, it's 3, so means 3 slots will be connected to R, okay, then rest 3, 4, 5, 6 to another, 7, 8, 9 to Y slot. Now you will ask me, sir, why not 10 and all that? Because see, the coil span, how much we told? Coil 1 is connected to coil 10. So now this 1 will be connected to 10, 2 to 11, okay, and 3 plus 9, you will write 12, okay, 3 plus 9, you will write 12, but you don't have a 12. Whenever you get this 11, again you come back to 1, okay. Similarly here, 4 plus 9, okay, 13, because you cannot connect that slot to the 12th, okay. So the maximum you can connect over here is like, you have a 36 slots. Now I'll explain you after it ends. This is 14, this this is 15, I'm adding 9 to it. Similarly, this is 16, this is 17, this is 18, okay. Then if I go to this I will add one 9, this is 19, this is 20, this is 21, okay, okay. So this is 19, this is 20, because I'm adding 10 plus 9, 19, okay. 11 plus 9, 20, and 12 plus 9, 21, okay. Here I forgot one, okay, I'll tell you. So this is 22, 23, 24, okay, 25, 26, 27, again here 28, 29, 30, 31, 32, 33, 34, 35, 36. This is perfect. I thought this is semi-closed type. Now I'll explain, okay. See, what happens is that now you have to draw the winding diagram. There I got confused, because some of the, if it is if it was open type, so we have to keep one gap, so some dummy coils will be there. But this is a very simple set of arrangement. So we know that there are 9 slots, okay. So, and the coil span, like coil per phase, so every winding will have, every winding would have essentially 3 slots. So first red I will give 1, 2 and 3, okay. Then I'll write my blue, okay, this is my blue I'll give 4, 5 and 6, and then let's take green, okay. Red, blue and yellow only will take yellow I'll give 7, 8 and 9. Now when I'm going to the second concern, so I have to add plus 9 to this, so it would become 10, 11, 12. Okay, similarly I have to add for blue also plus 9, so it would be 13, 14, 15. Again for the yellow also I have to add plus 9 because of the coil span, it's a full pitched. 16, 17, 18. So the total number of slots are 36. So I have to take until the 36 slots are completed. Again I have to add 19, 20, 21. Here again it would be 22, 23, 24. Here it would be 9, 16. How much it is? 25, 26, 27. Again here red, it would be 28, 29, 30. This is blue, 31, 32, 33. With now yellow is left, so it would be 34, 35, 36. So this is the winding diagram. This I can write this is my winding diagram with coil span of 9 and arrangement, that is your uh, number of, that is your number of slots divided by number of phases into number of poles. Now suppose the it was not 36, since here it is 36, so it came around 12 and 12, so it came around 3. So if it was not, it was 48, so here it would be divided by 12, it would be 4. So here I have to write 1, 2, 3 and 4. In that case, if it 1, 2, 3 and 4 and 4, 5, 6, 7, 5, 6, 7, 8, 9, 10, 11, 12. So this would be, and if the slot number is same, so like this it will follow until 48. Are you getting my point? Huh? Did you understand? Ratika, any doubt?
Yes, sir.
So suppose it is 60. At that time it would be 5. So the winding arrangement, because it's a very simple winding arrangement, it's a semi-closed. Usually you will get this type of winding arrangement in an examination, because the other type of winding arrangement you need to know the drawing. So this is it. This was about the class. Only 1 minute to go, so you can give your attendance, and if you have any doubts you can ask anywhere you have any doubts in the problem, like any doubts you have somewhere, like if you did not understand you can ask. So this was about the problem. We did the we worked out the winding details also. Yeah, any doubts you are having, Nilinakshi? Yeah, Afsa, Manohar,
No
any
doubt,
doubt?
sir.
Ajit Kumar,
No,
no, no, you are not having anybody should be having any doubt anywhere. Please feel free to ask. I took this is the last question I thought I'll do from induction motors. I'll cover everything. So most of the questions you have to practice it yourself. Suppose tomorrow it opens and there is an examination, and if you have to really enter an examination with invigilators, you have to be very good at it. Suppose they try to make a really difficult paper, whatever, how much ever difficult they will make, no problem. We have discussed every concept. Okay. The only thing that will help you in the examination is practice. So that's it. So from my side, so you please give your attendance, and those of you who have next class can join that class. So please, yeah, Likhit Gayatri. Okay.